Welcome to Design Night, Designistas. It's kind of like fashionistas, but we're Designistas here tonight. So we're really excited to host tonight's event, which is all about fashion. Design and technology have always driven fashion and vice versa. When you think about textile fabrication techniques and new materials, fashion is very often influenced by technology. Things like digital design and 3D printing are enabling designers to push boundaries and explore new archetypes. And tonight we're going to explore a lot of those concepts, first with our featured speaker, and then with our first ever Design Night fashion show. So we're pretty excited. First ever fashion show. Right. For all of you social media mavens out there, we hope you tag your photos and your posts with hashtag Design Night and at Autodesk Gallery. So without further ado, I'm going to introduce our featured speaker for tonight. His name is Francis Bitonti, and he's a multidisciplinary designer and the founder of Francis Bitonti Studio. He's ushering in really what's a new manufacturing paradigm. He uses innovative use of computational design techniques and emerging manufacturing technologies. He sees smart materials and interactive environments as opportunities to create new aesthetic languages for built environment. And he's also taken that vision and applied it to a wide range of disciplines, ranging from architecture to product design and, of course, to fashion. Francis studied at Pratt, where he has a Master's of Architecture. He is also a visiting instructor and a researcher there, and he teaches at RPI in architecture. He lives in New York and runs his design practice, and so we are thrilled to have him here tonight. Please give a warm welcome to Francis Bitonti.
Thank you. All right, thank you for that introduction. There's not much else for me to say. So my name is Francis Bitonti. I run a design studio in New York, in Brooklyn, or based in Brooklyn. It's called Francis Bitonti Studio. And as was just said, I'm a multidisciplinary designer. We work across a range of disciplines. Recently, we've become extremely focused on fashion. And I want to just start off and talk a little bit about the kind of journey into the fashion world and how we ended up here from the kind of work we started with. This is an algorithm called a cellular automata, and this is pretty much all I was interested in the beginning. The studio started doing projects in about 2007 before it was a formal entity. And I wasn't really interested in making anything at that point in time. What we were interested in is what the computer could do as a medium. One of the most important jobs that I think a designer has is that you're creating a formal language for your time, and in a way you're structuring culture through these forms. So form is very important to me. And the early work in the studio was really about exploring new and novel formal languages and not really necessarily with an emphasis on manufacturing, although that soon changed. So these are simple rules. You end up with a 1, a 0, or a 2. And what's amazing about it is you end up with images like this, and at first glance you might say, well, these are just triangles. And the truth of the matter is that, yes, they are just triangles, and you probably could draw patterns similar to this. But what's incredible here is that these emerged from a set of localized interactions. So nobody drew this, nobody conceived this image. It's a set of discrete, autonomous interactions with a set of agents, and that produced a clear, visible, global intelligence. So this research is the kind of unifying stream of all the work we do in the studio. And I always kind of position this work, with the Renaissance and with understanding the human body in relationship to the physical world. This is the Vitruvian Man, and this is a very particular way of seeing and understanding the place of a human being within our universe, right? They're using Euclidean geometry. He's inscribed within a circle and a square, and mankind is placed in the center of that pure kind of sacred geometry. If you look back at the Renaissance, right, so what was the idealized floor plan? I'm coming from an architecture background, so that's the analogy I'm going to pull, but it was a circle, right? And the reason for that is you're at the center of your universe, you're at the center of your world. Then Copernicus comes along and he draws this map, right? And this is a map of the solar system, and he says that the sun is the center of the universe. So then we get the Baroque, and you have ovals, and you have geometries with multi-centers. And whether or not this is a conscious effort or not, I don't think it is, but I think that essentially there's a kind of subconscious relationship between the kinds of forms we prefer and the kinds of forms we produce as designers that shape our built environment that have a kind of reflection to how we see our position in the world. So this other diagram is one drawn by an artist. His name is Stellark. And Stellark does a lot of interesting work on the human body, and he produced this diagram. And what's amazing about this diagram to me, and why I always show it against the Vitruvian Man, is because it shows the body within a network, right? So the body is just a node within many other nodes. It's not the most important node. It's just part of a larger system. And this is a map of the internet. And right, so this is kind of how we understand the world. This is how we understand our relationships to each other. Social media is by far probably the dominant, probably most interactions you go through are through social media, and it exists in a space kind of like this. So we're trying in the studio to come up with forms and formal languages, I call them formal languages, that are reflective of like who we are at this point in time and our culture. So these are just some early kind of images and explorations in form. Like I said, I was never really interested early on in making anything, and I would make these really kind of insane proposals like this, and I'd be surprised why they didn't want me to build it, and it was, and you couldn't. But then somebody said, well, why don't you try? And I submitted this bike rack design for the New York City Department of Transportation. They had an open call, and this is really what formalized the studio as an entity. We were selected as finalists, and the city asked us to build a prototype, and I couldn't, so I went to, it turned out to be impossible. I went to every type of manufacturer, I went everybody. I mean, the only people who would think about looking at this were sculptors, and I didn't want the human hand on it, because like I said, I was really interested in this idea of computational morphogenesis, form coming from the computer, and all that meant for the aesthetics of the object. And once you put a human hand on that and you see those traces of the hand and the reinterpretation through a human mind, not an augmented mind, I think we have an augmented mind now and an augmented body, it seemed really inappropriate, and the results that I was getting weren't things I wanted to be putting into the world. So I found a company called Red Eye, which is now a division of Stratasys. And they were printing car parts, and I thought, well, if you could print car parts, we could probably print a bike rack. So we printed the bike rack, and this is it. That's actually a photograph, it's not a rendering. These are some photos of it in the printer. And so I started thinking about, well, you know, this is a prototyping technology right now, but why couldn't this be a manufacturing technology? If we have a manufacturing technology that's directly linked to the computer that requires no tooling, so not only are we looking at a new sort of formal language, but we're also looking at a new manufacturing paradigm, a new way of buying and selling goods that's based on an object as being data, right? The object's not something physical, but just like you can send a PDF over the internet, I can send this object over the internet and print it wherever I want. So we don't need to ship things, we don't need to carry inventory. So this really changed the studio. It wasn't really just about form anymore, but it was really about engaging larger social and economic issues and really engaging in how things are made, how they're bought, sold, and distributed. And that would eventually lead me to the fashion industry as I tried desperately to find an industry that could support this kind of experimentation. This is the bike rack in Astor Place. It was ripped from the ground and stolen within 2 days, which I take as a compliment. And like I said, you know, so then now we're making things. So now I'm like, okay, well, let's see how we can make things. I'm not going to go through these because you're all here to hear about the fashion projects. But we were engaged in a lot of different types of computer-aided manufacturing as well as computer-aided design, and working really closely. We have a paperless studio. I don't draw. I can't draw, and I have no interest in it. Okay, let's go back. So this is the first fashion project we did. It's a belt. It's a stainless steel. This is stainless steel directly printed from a 3D printer. All the hardware is 3D printed, and even though I didn't have to, the strap is laser cut leather. We did this for a designer in New York. Her name's Katie Gallagher, and it's a relatively small brand. And for them to offer an accessory like this would have not been possible. I mean, prior to this technology, they could have never possibly made the investment in the tooling, especially without having sold accessories before. The investment would not have been possible. And also the complexity of the geometry. There's not one part on this belt that is not custom made. Each one is designed. You can't buy these parts anywhere. It's a completely one-of-a-kind piece. So we designed the dress, and we actually, not the dress, we got the dresses. We designed the belt, and we integrated it into their production pipeline, and it was sold in retail stores. And this was the first time I thought that, okay, we can actually do this, and we can actually work in a way with a model of manufacturing that's really unique and really different. So these are some shots of the belts on the runway. And some variations on the belt. And like I said, all of these are unique. All the hardware is unique. It's 3D printed steel. This is sadly I don't have process shots of the belt. It was a pretty rushed project. But this is we were working on a table. This is a piece of a table leg. So when you print stainless steel, it's actually a mixture of bronze and steel. So it actually looks like this, which looks like dirt, which isn't really very attractive. So finishing is a big issue with this. And a lot of people will always ask, well, what's going to happen to all these jobs? And the truth is there's still craftsmanship, things still have to be made, material has to be manipulated, and that's never going to change. But the types of materials you're working with and the materiality is going to be different, and designers just need to be aware of this. And I don't know how much awareness there is. All right. So we did two versions. We did one in black and steel, and we did one that was coated in bronze. And like I said, all the hardware, all the connecting pieces, nothing was bought off the shelf. It was all made unique. So the following season, we continued the collaboration, and we started working together on some garments. We started working together on textiles, as well as accessories. And these are some of the garments we collaborated on, and these are laser-cut textiles. This is one of the sleeves. It's a close-up of the sleeve. This is the shot of the skirt on its own. And the concept here when we were working together was that we wanted to dissolve the silhouette of the body. So we wanted the body to disappear into the atmosphere. So really the role of the studio was to start to find geometry, ways of manipulating material that would achieve this effect. And I love this shot because I think it really shows that we were successful. This is the coat. So what we did for this project was this didn't really involve 3D printing, but we digitized her patterns. We digitized Katie's patterns. She gave us a set of traditional dress patterns. And we used them as a container for an algorithm similar to how birds would flock. And that helped us develop this really, there's obviously a lot more operations here, but it helped us develop this really intricate ornamental geometry that was really responding specifically to the container of the pattern. So there was an intelligence in the system that allowed us to develop specific geometric organizations and characteristics that we wanted to have in the garment. So again, and just dealing with this new manufacturing paradigm, these patterns could be customized on different orders. If you rerun the system, you generate new tool paths. Things aren't cut with a die. Nothing's set in stone. And because it's all software-based and data-driven, everything can be different each time. And some of the effects we got, like we wanted to have these sort of like wrapping around the sleeves. And there's a lot of these really beautiful moments in the garments where you can see the awareness of the shape of the container and how that influences the design. We also worked together on another set of belts. Again, working with this idea of dissolving the silhouette. We saw the center of the body as a meridian, a dividing line, and we didn't want a hard line there. We wanted something that would be softer and something that would make a smooth transition from the top and the bottom of the body. And these are the backs, some of the looks on the runway. All right, so Adidas Dress. So this was a really great project for the studio. We collaborated with Michael Schmidt Studios in LA. And it was a collaboration between my studio, Michael Schmidt, the Ace Hotel, and Shapeways, based in Long Island City. The entire garment is 3D printed. There's over 3,000 unique articulated connections. It's flexible, and there's 12,000 crystals on it. And the whole thing weighs about 11 pounds, which is actually 70% lighter than her normal stage wear. And like I said, each one of these articulated connections is unique. So it's deforming. It was generated from a digital model in 3D to a model of Dita's body. All the curvature is different. Each little length of each segment is unique. It could have never been put together. On the one hand, yes, this is a chainmail dress, but the complexity in the dress is far beyond what any human being could do. You would need to have an augmented kind of manufacturing process in order to put this together. So Michael came to me initially with this concept of creating a dress based on the Fibonacci spiral. We started out by placing these spirals on the body, and one of the things we realized was that if you were to kind of put the spirals mirrored to each other in 2 dimensions, you would end up with this diamond grid pattern that you see in the dress, which was great because 4-sided shapes are really good for articulated flexible fabrics. The thing that we realized, though, was that, okay, that's a 2-dimensional diagram, but we needed to figure this out and how this would work in 3D. So we moved the spirals to wrapping around the body in 3 dimensions, and you ended up with this very similar structure to kind of like a Chinese finger trap. So then I should probably add, me and Michael never met in person until the dress was unveiled. The entire dress was designed over Skype. So I would sit in my apartment with a laptop facing my computer, and anyway, we went back and forth like this for about 4 months working on this dress. So you'll see here that this is a very low resolution version of the dress, and there's a lot more complexity in the dress than what you see here. The reason for that was that we needed a way to work together, so we had to work on a low resolution version of the model that could then be converted into the high resolution version quickly. And having a limited number of polygons, we designed the entire dress in Autodesk Maya. It made it very easy to manipulate the form quickly over Skype to Michael's specifications. This is an earlier version of the dress that I really liked. So just to give you a sense of what I'm talking about, of why you would work with a lower resolution, because being able to, if we build off of this polygon mesh, you'll see that the densities in the low polygon mesh, as you subdivide, you can dictate density and where you want more density versus less. So you'll see that towards the top of the dress, we have more polygons because we wanted that to be more dense, obviously, to create privacy. And as you get down, we wanted it to open up. So this is again, these are more screenshots of the dress of us in the working environment. Now this is the high resolution version, which would be much more difficult to edit. But you'll see what we did is we actually worked in a way where we could structure the polygon mesh to mirror the way we wanted the articulated fabric to work. And then these are some earlier design sketches and iterations of that. This is one of my favorites. Okay, so because we're working, like I said, so this is the kind of base structure, right? So now we have a diagrid that looks the way we want it to look, and it functions the way we want it to function, but we needed to then model, like I said, there were 3,000 articulated connections, and that's a lot of geometry because these are all curved. And circles, anybody who's a programmer or deals with this stuff knows that that's very processor intensive. So we needed to be able to build the complexity up through a component. So what we did was we developed a tile, which when mirrored over the body would complete what would become the articulated fabric. So we actually didn't design it. We just set up a framework for it to exist within, and then we created 1/4 of what would be the completed articulated component. This is a close-up. So the files were then printed at Shapeways in Long Island City. These are the EOS laser sintering machines that printed the machine in their factory. And again, like I said, there's a lot of craftsmanship and there's a lot of skill in being able to excavate these things. These were, the thickness of each of these members was about 0.5 millimeters. So it's very strong, but when it's packed with powder like you see here, this is actually how it comes out of the machine. It's a very time-consuming process to remove and excavate. So this is the first pass, still totally caked, and then this has to all be cleaned out, and it's quite a messy process. And like I said, because this is flexible, this is a rigid piece. The shoulders were rigid. Let me get to one of the flexible parts. So this is the flexible part over here. Like I said, we hid that jump ring that was creating the flexibility. So that was all surrounded in powder, and it was very tight. I mean, it was less than a millimeter gap. So those all had to be cleaned out one at a time. It was a 3-day process to get this from the machine to Michael Schmidt Studios in LA for assembly. So this is the fabric after it comes out of the machine. So you can see it's very flexible, very fluid. And it's all printed in one piece, and every piece is unique. So they were all cleaned up, packed up, and then shipped off to LA. These are the boxes. And then once they got to Michael Schmidt Studios, we 3D printed a jump ring that could be connected. We couldn't use any off-the-shelf hardware because this was all, we didn't want to see the articulation. We wanted it to just look like lines on the body. So they were very tight, and because of the tolerances, we needed a custom fabricated ring. So there was really no margin for error. Everything had to be perfect. This is just to show how thin it was. This material was perfect because it's dyeable. So this is the material dyed black. It's a laser sintered nylon. Not only is it dyeable because it's laser sintered, it's not brittle at all. It's very strong, and it's actually almost flexible. You could squeeze it and it'll return back to its original shape. So it had a lot of desirable properties for this project. This is the detail of the shoulder with the crystals applied. And this is how it moves. So it flows and drapes like fabric. It moves with the body. She's able to walk, dance, do everything she needs to do. So let's talk about some of the projects we've done since Adidas Dress. This summer we collaborated with Makerbot and Pratt Institute. Pratt has a research center called the Digital Arts and Humanities Research Center. And Francis Bitonti's studio, the research center, and Makerbot worked together to do a workshop on computational fashion. We wanted to take a group of interdisciplinary students, give them a crash course in 3D modeling and computer-generated design, and a bunch of 3D printers, and let them make a dress. It was really fortunate timing. We worked with Makerbot, and they were just about to release a new filament that's flexible, which you could imagine we were really excited about. So this is us in the classroom. This is just some shots of us talking, no reason. So one of the things that they were working with is, I talked earlier about this sort of, these swarms running within the patterns in the Katie Gallagher project. And we wanted to take that idea a little bit further here. And we 3D scanned a model, and we used her body as a landscape for these agents to swarm on and flock and move. And so the body becomes a container for the algorithm. It becomes something that you can run the algorithm on, and a place to experiment pattern and form. So this is a screenshot of one of the students' work, and we worked with Casey Ream on this as another one of the instructors who helped a lot with the coding. So these are some shots of students' screens, students' work. And like I said, we worked with Makerbot, and this was amazing because typically I don't have this luxury of being able to print while I'm working. Usually you do all this design work and then you send it off for a really expensive print and you hope it works. What was great about working with the Makerbot and having it on the studio is, like I said, this is a new kind of materiality and a new way of working with materials, and the students were able to really experiment with not only what was being printed, but how it was being printed. The software in Makerbot lets you control a lot of things, like how the infill is done, what temperature you're printing at, how the layers are laid down. It opened up for us another level of material investigation that I don't think very many people who do this kind of work have had the opportunity to really look into and experiment with yet. So these are some of the experiments the students did on the first week. Like I said, it was just a crash course, and just get them outputting, get them excited, very kind of organic, and we did some fabrics. These were all printed on Makerbot. So after the first week, we taught them a lot of software. We taught them Maya. We threw a whole range, and they were about ready to have a mutiny. But it was important, because then the following week, what we asked them to do was we asked them to work collectively in groups and formulate a design agenda, formulate a design proposal. And even though we only got surface level on all of these techniques, it enabled them to know what was available. And then when it came time to produce the project, they were able to dive down into greater detail on all of these techniques. This is one student. They were working with an algorithm that simulated electric fields. And they were imagining the body as the landscape of electrical current and generating lines like that. There was no sketching. It was important that this was a paperless studio. Some more experimentations of the students, and printing experimentation. So we brought in a model in the second week, and we did a body scan. We actually scanned her with the Kinex. So some shots of her. We took her from all different angles, reprocessed the point clouds, and we made a 3D model that the students would take as an initial condition. This is a video of some of the algorithmic work that the students had done. So you can see here, it starts in blackness, but what's guiding this is the body. So the agents in the system are learning from the body and developing curvatures from that. So what we really try to do is we're trying to really transform design methodologies in the fashion industry. Typically they'd be draping fabrics, and as I said earlier, we want to be developing new kind of formal and aesthetic languages through these tools. So it's important that the students let that stuff go. So this one's a little bit interesting. You can see they're letting the agents leave the body. You're getting more of a fuzzy silhouette. It's not really so clearly defined. We can't exactly tell what it is like you can in the other one. So at the end of the second week, they all produced their own design. There were 4 groups. This is one of the designs. This group is working with electric fields. This is another one. This student they were using animations actually in Maya. They were creating animation snapshots and freezing the animations. These are kind of similar to those early Muybridge drawings. This group of students they took the material investigation very seriously, and they tried to create a flexible, articulated fabric, like a set of living hinges, using tessellations from the subdivisions in Maya. This group was working more closely with the coding algorithms. So in the end, we invited a jury in, and they said my hope was that they would choose one project and we would build that, but instead they decided that they liked 2 projects and they wanted the 2 to work together. So the 2 groups worked together and they produced this final design. The design was then broken up into parts that could be printed on the Makerbot, and they printed a series of parts. Are we okay on time? Yeah, okay. And then in the end, after the dress was fabricated, we had a photo shoot with the model who we originally 3D scanned. This is her being dressed, hair and makeup. I always love this video because when I sent the photographer inspiration for the shoot, I sent him a lot of clips of old vampire movies. And I love in those movies how the shadow becomes another character. And then she was dressed. The dress is made in 3 parts, and it laces up along the side. And this is the final dress. So next week, the design will be put up on Thingiverse. And I don't know how familiar you are with Thingiverse, but Thingiverse is an online platform where people can upload their designs and download and print them out on a Makerbot. So this dress will be available to the public. So it's an open source garment that's made in a plant-based polymer that's shareable, editable, downloadable, and you can make at home for under $400. So it's pretty cool for a group of students. Yeah. Okay, so this leads us into our most latest investigations. This is an MRI of a human body. And I'm looking at this because I'm designing a handbag. And I'll tell you why. So what's great about an MRI is, okay, just like a 3D print, just like a digital file, when you make a 3D printer file, you're abstracting the physical world into a type of media, right? And once it's media, you can send it all over the world, you can share it, you can edit it. It's incredibly powerful. It's not a physical thing anymore. There's a level of abstraction there that's really liberating. So what's happening here is, right, we're looking at different colors, and those not different tones, not even colors. Those different tones are telling us that something's bone, or something is fat tissue, or something's organ tissue. And then that is what enables an MRI technician in order to create filters so you can look at different parts of the body and find different types of anomalies. But the important thing here is that you're abstracting the physical into the virtual so that you can perform an analysis. Going backwards. So this is the handbag we're working on. It's going to be, the structure of the bag is 3D printed. It's going to be a merger of traditional craftsmanship and high-tech kind of next generation manufacturing. The metal is all going to be 3D printed, and it'll be assembled at a factory in Morocco where the stingray leather will be applied. This is the clutch. So this is how the bag opens. So you can see it kind of wraps up around, and this flap has to flex, right? So for that to happen, and most 3D printed materials, if you've noticed, are rigid. They're usually rigid polymers, so that's changing. So where you see these striations, I'm just using this as a diagram. That's showing you where we need it to bend. So what we had to do was create a living hinge. So we started working with Stratasys, and they have a technology. It's actually out here in the exhibition space. The Connex 500 is the printer we're working on, and what's incredible about it and what drew me to it is that you can print more than one material at a time. So this is printed in one piece. It's a living, flexible hinge, and the bag comes out with all of its flexible parts fully assembled. Because we want this to be a commercially viable product and not a prototype, we spent a lot of time thinking about how we could distribute this material so that it would be strong enough to withstand daily use. So we did a number of tests, a number of ways of integrating the rubber with the rigid materials, and we found a solution that works. And the solution is pretty simple. We just would, you'd have the rigid material on each side and the rubber in the middle, and then a very thin layer of a rigid material on top to reinforce it. But that wasn't really enough, actually. Wasn't enough for me. We wanted to take it a little bit further. In working with Stratasys, we realized what we could do is we could print from bitmaps. Bitmaps meaning images. So we're not limited to working with geometry at this point, right? So what we're doing is we're working with a set of still images. This is how flexible the hinge ended up in the end and bendable. This is a cross-section through that hinge. Okay, it blurs, right? So you start with one material, whatever the white is representing, and you're getting to the black at the end, right? So there's no hard there's no hard dividing line between materials. You're continually transitioning from one to the other, and it gave us a lot of strength, and it made a really amazing material for us to work with. So going back to the body again, right? This is really similar. The bone is white, and you're dictating different materials and different material behaviors with different tones of gray. So that got us thinking, could we make textiles in this way? So we opened up another line of investigation with Stratasys in the studio, wondering if we could think about material construction in this way where things are continually, the kind of composition of material is continually transforming in the cross-section. This is the conceptual rendering. Now, this is an animation cutting through all the sections vertically of that textile. There's only two colors here, but the color difference you're seeing is because of the mixing of red and white. Okay, so the rigid material is white, the flexible material is red, and all the hues of pink are different degrees of flexibility. So it's incredibly powerful. And when you start thinking about how you could structure a garment, right? If we think about Dita's Dress, where we're limited to what is a pretty old technology, basically chainmail, albeit highly customized and far beyond what a human hand could create. It's not the same as this is like something you would find in nature, a material that's continually differentiating itself. And it can be printed, again, with all the kind of benefits of this type of manufacturing that I spoke about earlier. These are some close-ups of some of the prints that we generated from this research. So you can see there's a differentiation, like those clear white spots, they're the most rigid. And because we're working this through algorithm, we're not really worried. I'm not really having to deal with my own mind. So this incredibly complicated form actually flexes and bends, and we have samples of them out in the gallery. And why did that happen? All right, well, this is just showing it on a dress form. We haven't gotten to a full garment yet, but I just wanted to share this with you. This is another image, again, of varying complexity. The material differences are not quite as apparent in this one. I'm going to just jump. So this one, it is. So you can see towards the bottom this gradation and different degrees of milkiness where the rigid materials are being integrated with the flexible, different veins of flexibility. It's an incredibly complex set of living hinges that are making up a fabric. This is a close-up detail, and you can see all the not only the differences in geometry, but the difference in material composition. And this is all complexity that can be managed in a way that can be mass-produced, which I think is absolutely incredible. That concludes my talk. Thank you.